Hello, hello, hello. And I forgot to record all of that. Anyway, share screen. So I hope you all can see our introductory slide. Again, my name is Professor Rob Parks, and this is the first of a series of talks that we plan on giving approximately alternating every Tuesday evenings, starting from 7 p.m. Onward. This is the first time that we have done this format. Prior to during the pandemic and during lockdown, we would do these events completely virtually. But now that COVID is hopefully getting behind us, we're starting to open up and do in-person tours. And right now we're moving to a hybrid mode. So there are folks here in person, and there are also a couple of folks who are with us virtually. The way that the Evening Under the Stars event is structured is that we will have a 30 to 45-minute talk by a professional astronomer or someone related to that field. And then we'll have a small or short Q&A afterward. And that is followed up by a 30-minute guided tour of our observatory. Now, tonight, because weather is not kind to us, we will be doing a virtual only tour, where we will essentially be showing you canned or images of objects we've taken with the telescope over the past semesters, to give you an idea of what the telescope can actually do. And we will also talk about what the telescope is and how it's designed. The telescope is located here on campus on Research Hall. You might, if you're a student here, you'll see the silver silo looking thing right next to Research Hall. The dome on top of it is where our observatory is held or housed, and it is controlled by a control room off to the side of the roof. But it can also be controlled virtually. So one of the, I guess, silver linings of the pandemic is that it accelerated our program to actually make things virtual. So now, if you have an internet connection and the right permissions, you can operate our telescope from anywhere you have internet. Which has been very, very handy, particularly in times like this. The images that you see, hopefully see around the screen, those are images taken using our telescope, taken by students who are friends of the observatory or the photo club. These are a little bit outdated. I've been meaning to update this slide to show some of the tremendous work that's been done more recently. This is not a one-person operation. Again, my name is Rob Parks. I'm the deputy director. Dr. Peter Plavchan is our director for the observatory. We have been blessed with 4 graduate teaching assistants this term. We have Kevin Collins, M. Thanyapong, Mohammed El Mufti, if I'm pronouncing that correctly, and Patrick Newman. M will be the graduate student on deck who will be providing the telescope tour at the end of the talk today. We also have tour guides listed there as well. I do want to highlight the Friends of the Observatory organization, run by the current president is Jonathan S. They have monthly meetings. They have access to the telescopes that we have here at the observatory, primarily the 32-inch George Mason telescope. They have frequent day and nighttime telescope viewing. Yes, they actually have a solar telescope, so you can actually see the sun during the day on days that just have the feeling to go out and look at the sun. And also, we are now working with them. Peter and I are now working with the club to find dedicated nights where the club can actually take data using our 32-inch telescope and do astrophotography with it. Excuse me. Like the image that you can see on the bottom right. That image was remarkable not only because it's a set of images taken using our telescope to make that nice, pretty 3-color image, but if you look closely enough, right there, they were fortunate enough to actually capture a supernova as it went off. So if you're interested, if you're a student of George Mason and are interested in astronomy and interested in talking with other folks who are, I highly recommend finding this club, that QR code, if it works, brings you to their Discord. If you're interested, if you're a student or not, and you're interested in what we do here at the observatory, both from a research, from a teaching, or from an outreach standpoint, I highly encourage you to sign up for our free newsletter, the Moon, the Mason Observatory Outreach Newsletter. And if you see, and if you, by looking through there, you really like what you're seeing in terms of what we do here at the observatory, we also would ask that you might consider becoming one of our patrons. One of the things that we are really trying to get off the ground is a enhanced or a much larger outreach program than we had previously. And unfortunately, that requires a bit of funding. And so in order for us to reach areas of the surrounding areas that are typically underrepresented, or they are very rural and just do not have the resources for telescopes or visiting observatories or planetariums, we would like the opportunity to go out to them and actually allow them to use our resources for that. Here are some of the levels at which you can participate. I would very much like to highlight one patron, Eileen Craigie. She has recently become a Big Bang patron. Recently, she has helped us a great deal in terms of our outreach motivation, primarily in terms of light pollution. She is very much interested in trying to curb the amount of light pollution that is in this area, particularly on campus. And so without her contributions, without her involvement, I don't know where we would really be recently or today. So with all that out of the way, let me introduce Dr. Amber Stuver. She is an assistant professor of physics at Villanova University and a member of the LIGO scientific collaboration since '99. She specializes in the computational aspects of gravitational wave searches with experience in data analysis design, gravitational wave simulation, detector characterization investigations to minimize the impact of noise in the search for astrophysical signals. You'll be hearing, not to spoilers, but you'll be hearing something very cool later on in her talk. Besides teaching and research, she is a fluent science communicator, having given tours to thousands of visitors to the LIGO Livingston Observatory and speaking at many venues and writing content for outlets like TED-Ed. So without further ado, I will turn it over to Dr. Stuver, and yeah, I hope to give her your attention.
Hi, everybody. My name's Amber. Hi from Philadelphia. I wish I was actually there with you someday. Maybe I'll come back and visit you all. That would be awesome to see you all in person. Let me share my screen. So I'm going to be talking to you today about gravitational waves and how these gravitational waves are opening up a new field of astronomy called gravitational wave astronomy. And this is fundamentally different from the way astronomy has been done traditionally. But first, let's talk a little bit about what gravitational waves are. So gravitational waves, I remember whenever I first started getting interested in them, a lot of scientists will just say, oh, they're ripples on space-time, as if that's going to make sense to everybody. And of course, I didn't want anybody to think I didn't fully comprehend everything they were saying. And early on in graduate school, I mastered the shaking my head and the deep understanding phase. But it really wasn't until I was in actually taking general relativity in graduate school that I got a better understanding for what space-time really represented. And that's why I have this animation that's going on the right side of the slide. What you're looking at are two neutron stars that are orbiting each other, colliding and merging. Underneath that, you see a green grid, and it has ripples on it. And this grid is representing space-time. Space-time, the slope of the curvature, so how much it deviates away from flat, indicates the strength that gravity would be at that location. And so instead of just saying that gravitational waves are ripples on space-time, another way of thinking about it is that gravitational waves are just changes in the gravitational field that are propagating out into the universe. And so that's what you're seeing on this looping animation of our two neutron stars merging. This is analogous to things that we see in everyday physics. And one of the everyday physics things is that electromagnetic waves or light are created whenever an electron is accelerated. And gravitational waves are actually created whenever mass is accelerated. So just like electromagnetic waves are propagating electric and magnetic field, gravitational waves are propagating gravitational field because of the acceleration due to mass. So you might think that since if it's just mass that is creating these gravitational waves, anything can create a gravitational wave. Me shaking my fist at a driver that cuts me off in front of me, that should be making a gravitational wave because my fist has mass and I'm accelerating it. But since gravity is the weakest of the fundamental forces, gravitational waves are also going to be exceptionally weak. So only extremely massive energetic events will produce detectable gravitational waves, at least detectable here on Earth. And some of these examples of these extremely massive energetic things that happen are things like the Big Bang, a star exploding in a supernova, a compact binary merger, and that's also what we're seeing in this neutron star merger. Any compact object, so it could be things like neutron stars or black holes, any of them merging together. These are examples of sources that would produce gravitational waves that we would be able to detect here on Earth. So we're not worried about detecting with gravitational wave detectors, at least, gravitational waves from earthbound or terrestrial sources. This really is something that is very well set up to be a gravitational wave observatory instead of just detecting mass moving around on the Earth itself. So, sorry about that. So, let's talk a little bit now about gravitational waves and astronomy. So I mentioned that some of the most violent energetic things are going to be good for detecting gravitational waves. So that kind of lends itself to what's out there in the universe. We're going to have a chance to observe the universe in a way that we've never been able to before. So gravitational waves, since they're produced by mass moving around, it's going to bring us information directly about how the mass is moving in a system. And this is something that light observations very rarely do. So this will allow us to observe objects that do not produce EM radiation at all, so that don't produce light. We'll be able to observe black holes directly. Black holes are called black not because they're actually the color black, but because no light can escape from a black hole, so we can't observe them. There's no light coming out, so it's dark. We call it a black hole. With gravitational waves, we're going to be able to directly measure these black holes moving around just because they have mass. It doesn't matter that they're not producing light. Another amazing thing about gravitational waves is that the universe is essentially transparent to gravitational waves. So basically, a gravitational wave comes by and it passes through an object unchanged and continues on its way. Basically, nothing can block our view of a gravitational wave. There's no such thing as a gravitational wave shadow. So this is an advantage over light because even diffuse amounts of dust between us and an object we would like to observe can cloud or completely obscure our view of the thing we would like to observe, at least if we're observing it with light. With gravitational waves, this isn't a problem anymore. Another really awesome thought that we're still a bit a ways from, but it is possible with gravitational waves, is that gravitational waves can allow us to see farther back into the history of our universe than we've ever been able to before. So, for example, the cosmic microwave background is the leftover light from the Big Bang. And this light started propagating freely throughout the universe about 300,000 years after the Big Bang. That's whenever the universe became transparent and light could propagate freely through it. Gravitational waves, on the other hand, the universe became transparent to them about 10 to the negative 36 seconds after the Big Bang. Essentially, the instant after the Big Bang, gravitational waves were able to propagate freely throughout the early universe. And just like we can detect the relic light from the Big Bang, we hope to be able to detect the relic gravitational waves from the Big Bang. And if we do, it will let us look back into the history of the universe to almost the instant after the Big Bang itself. So these are some of the big things that gravitational waves bring to the astronomy community, or should I say add to the astronomy community. And this isn't going to replace traditional observations that are made with light in its different forms. Instead, it's going to complement it. If we can observe the same object in multiple ways, for example, in both light and gravitational waves, it's going to give us a more complete picture of what is going on with that source, give us a better understanding of what's going on in the universe. And we actually have an excellent example of that I'm going to talk about a little bit later in my talk. So, next slide. So let's talk about how gravitational waves affect space. So gravity is a tidal force, and I like to talk to my students about tidal forces. If you think about how the gravity causes the tides on the Earth, you have low tides where kind of the oceans, and actually all of the Earth, but it's easier to notice with the oceans, are squished along one axis. That's where low tide is. And then it is drawn out on the orthogonal axis, or at a right angle to the low tide axis. And that would be where high tide is. So gravity in general causes this squishing and stretching effect. And this is exactly what happens when a gravitational wave passes through space as well. So a gravitational wave is a transverse wave, and a transverse wave just means that whenever a gravitational wave is traveling in a certain direction, so you can imagine a gravitational wave traveling directly out of your chest, for example, then the stretching and compressing isn't going to be in the same direction as the gravitational waves are traveling. Instead, it's going to be in the plane that's perpendicular to the direction of travel. So basically, you could imagine having a bunch of sheets of paper, and the arrow that is the gravitational wave just shooting through each one of those. And it's the surface of the paper where this stretching and compressing would happen. So along one axis, you have compression. Along the other axis, you have a stretching, and it alternates back and forth like this. So this is the effect that a gravitational wave is going to have as it travels through space. And with this in mind, we can build a detector that can help detect this stretching and compressing. To do that, we've built interferometric detectors. So actually, let me back up a little bit. Let me talk a little bit about the LIGO project. So up in the upper left-hand corner, you see that I have the LIGO logo up there. And LIGO is an acronym, and it stands for the Laser Interferometer Gravitational Wave Observatory. So you can kind of understand why we decided just to go ahead and make an acronym out of that, because that is a mouthful. But it is a very good description for exactly how our detector works. So the I in LIGO stands for interferometer. And what an interferometer does is it splits light into two equal parts. It sends it down, or orthogonal axes. So an L-shaped detector is an interferometer. It sends the light, the equal halves of the light, down each one of those arms that are at right angles to each other. It reflects the light from the very end using mirrors. The light comes back, recombines at the corner of the L, and we can measure the brightness of the light there. If the light is just as bright as the light that we put into it, then we know that the arms of the interferometer have not changed length while the light was in the arms. However, if the light that comes out is darker, so if it's dimmer, if it's not as bright as the light that we put in, we know that that's because one of the arms or both of the arms have changed length relative to each other. So that's what an interferometer is. The light that we use inside of our interferometer is a laser. So that's Li, a laser interferometer. And then we apply this interferometer to detect gravitational waves. So that turns us into a gravitational wave observatory. And we're truly an observatory because we want to do astronomy. There are 2 LIGO detectors in the United States. The first one is in Livingston, Louisiana. This is about 45 minutes east of Baton Rouge. And that is the image that is on the left-hand side. You can tell that all of the scenery around there is green. We're all the way out in the woods because we want to be away from civilization as much as we can realistically be, because civilization makes noise, makes vibrations. And we want to be as far away from those vibrations as possible because the gravitational waves we're looking for are so weak. So we're, besides looking for gravitational waves, we're almost the most sensitive microphone on the planet because we're so sensitive to vibrations coming from anything. So that's why we're all the way out in the sticks in Louisiana. So Louisiana is very wet, it's very green, and that's in contrast to the other LIGO detector that's in Hanford, Washington State. And this is on the site of the Hanford Nuclear Reservation. This is where they refined the plutonium that was used for the second atomic bomb that was used in World War II. So this was a lot of land that the government already owned. And since this is the largest project that's been funded by the National Science Foundation, and this is your taxpayer dollars at work, we would much rather spend those resources on science than real estate. And so the government said, would you like to put LIGO here for free? We did studies making sure that the vibration levels were acceptable. And then, yes, we would. We would very much like to put it there. So it's in the high desert of eastern Washington. Each one of the arms that you see here is 4 kilometers long. And in our everyday experience here in the United States, 4 kilometers is just shy of 2.5 miles. And that's one of the reasons why we needed to take aerial pictures to put on this slide. And even then, you don't get both of the arms completely in view in either one of these shots. Sorry, I couldn't find one with both of them completely in view. But these are the interferometric detectors. These are our gravitational wave observatories that we use here in the United States. There are also international detectors that we collaborate with. There's one just outside of Rome in Italy called the Virgo detector. And there's another one in Japan called Kagra. Anytime we're taking data at the same time, we all share our data together. Our collaboration isn't about who sees something first. It's about all of us, as many of us as possible, seeing the same thing so we can extract the most science from it. So it's very exciting getting to work in this international collaboration where politics is more an afterthought, or at least left to the politicians. Science, where we're more interested in detecting gravitational waves. So let's look inside of a detector. So we're looking here at the source of our laser light. At the corner, it is split into 2 equal pieces. We're following one of those pieces down the 4-kilometer arms. It reflects off of a mirror at the end and recombines back at the corner, and we read the brightness at the end. That's what's on the right side. If the arms change length, so you'll notice the little arrows where the mirrors are moving, so the arms are changing length, then at the output of our detector, our waves are from the light from each of the arms are either going to be in sync or out of sync. If they're in sync, it's going to make the light bright. If they're out of sync, it's going to dim the light and possibly make it go completely away. That's called destructive interference. And so we can measure how much the length of our arms in LIGO have changed in order to look for a gravitational wave. And to give you an idea of how small of length measurements that we're making with LIGO, we're looking for gravitational waves that are about 1,000 times smaller than the diameter of a proton. So think of an atom, and then whenever you strip away the electrons and you're left with the itty-bitty nucleus at the center, that's made up of protons and neutrons. Pluck out one proton and then divide that up 1,000 times, and that is about the size of the length change of that a gravitational wave will make to our detectors. So these are also the smallest length measurements that humans have ever made. And we do this on a daily basis just because we're looking for gravitational waves. And to be perfectly honest, I worked at the Livingston Observatory for 10 years before coming to Villanova. And I think I was the only person there who bragged about that to people. And I will brag about that to anybody who will listen. All right, so let's talk about our very first discovery of gravitational waves. So it was mentioned at the beginning that I've been part of the LIGO collaboration since 1999, and we made our very first detection of gravitational waves in 2015. So I went about 16 years working on LIGO and seeing absolutely nothing. And then this came through our detector. We had just gotten done putting in major upgrades to our detector. And the very first day that we turn it on, whenever the data is of good enough quality to do science, this comes in. This actually came in about 10 till 5 in the morning on the very first day we collected science data. So what you're looking here at is data that was collected at the LIGO Livingston Observatory. And then what you see here is data that was also collected at the LIGO Hanford Observatory. And if you look at this, you'll notice that these two signals look very, very similar. Typically, whenever you look at any two segments coming out of our two LIGO detectors, you're going to see random noise. You're not going to see something that you look at this and go, that's the same signal. And our data analysis methods, so the computer programs that we write to look for gravitational waves, caught this very quickly and nearly lost their minds. And everybody got so excited that we actually almost didn't believe this at first. The higher ups in LIGO in the past have put fake gravitational waves in our data to test if we were able to even find them. If you've never found a gravitational wave before, how do you know that you're not missing a bunch that we should be seeing, but our data analysis methods messed up? So they put fake signals in our data previously, and they made us find them. And they made us, not only did they make us find them, we did find them, and they even would not tell us it was a fake signal until after we wrote a paper and were ready to publish it. So when this came through, we're like, well, this is too good to be true. I bet this is what they call a blind injection. That's that fake signal they put in to test us. And the emails were going around in the collaboration. The higher ups in LIGO actually broke into the email conversation and said, you're giving us a little bit too much credit for being prepared to do such a fake signal this early in our science run. Remember, I said this was the very first day. And basically the message was, this is not a drill. And so we spent the next 5 months actually trying to disprove that this was a real gravitational wave. We even interrogated the old guys who had the knowledge to actually fake a gravitational wave. Basically, the old guys who would benefit from getting a Nobel Prize before they bought the farm, they got interrogated to make sure that they didn't. And that was just part of the part of all of the investigations we did. It's not all human investigations. Most of them were statistical and trying to associate this signal with a Earth-based signal, and we absolutely couldn't. And that's whenever we made the detection announcement. If you look really close here, there are predicted gravitational wave signals, and this prediction that is on top of what you're seeing right here, it's actually fits so well it's a little bit hard to see, but this prediction is for two black holes that are each approximately 30 times the mass of our sun, going around each other, getting closer and closer together, getting faster and faster, and finally merging. And so not only did both of our detectors see the same thing at the same time, which is an expectation for a real detection, but we also have a good idea of what this is just from our data analysis methods that use these banks of predicted gravitational wave signals. We knew right away that this was a binary stellar mass black hole. Stellar mass meaning that it is less than 100 times the mass of our own sun. So let me pause this for just a minute. So what you're about to hear here is actually taking the data from LIGO and making it audible. So gravitational waves do not make sound. That's like sound waves are completely different than gravitational waves. But just like you can take radio waves from the air and then a radio can put it through speakers and you can hear the music that's carried on them, we can take gravitational waves that we detect with LIGO and we can put it through speakers and we can hear them. And so this is what the gravitational waves the very first detection, what it sounded like. So you can see here the data on top is from LIGO Hanford. The data on the bottom is from LIGO Livingston. We put the waveform so that goes along with the time. And we also put how much of the signal was in what different frequencies. So on the y-axis for each one, for Hanford and LIGO, we have what frequency the signal was at that specific time. And you might look at this and go, well, why does that just sound like a thump whenever this is actually ending up at about a middle C frequency on a piano? And the reason for that is because there's so few cycles, there's so few repetitions of that sound that we hear more of a thump than we actually hear a tone. So what we did to make it a little bit clearer to hear is we actually increased the frequency about 400 hertz, and that is what this is. So this is the gravitational wave equivalent of a false color astronomy picture. And that whoop sound, that's something that we like to call a chirp. That is the characteristic of a gravitational wave coming from two objects that are orbiting around each other and then merging to become one. And that shh noise in the background, that was just detector noise. So anytime you do science, anything you measure that isn't what you want to measure is called noise. And like I said, LIGO is extraordinarily sensitive to any vibration coming from the environment, and that little bit of vibration coming from the environment is what's making up that background sound. If we were out in space, we would not be able to see the two black holes. However, the black holes would bend the light coming from sources behind them in an effect called gravitational lensing. And this is a simulation, so that nobody actually really saw this, but this is a simulation of what two 30 solar mass black holes, what the gravitational lensing from those would have looked like. So you were able to see both of the black holes going around each other, and then they eventually merged and became one black hole that's about 60 solar masses. Then in 2017, something even bigger happened. So there's satellites orbiting Earth that are looking for gamma rays. And there are strong outbursts of gamma rays that come from the universe on a regular basis. These are called gamma ray bursts. They come in two classes, short gamma ray bursts and long gamma ray bursts. We have a good idea of what is actually producing long gamma ray bursts, but we really didn't know what was producing these short gamma ray bursts. And there are hypotheses that said it could be two neutron stars orbiting around each other, merging together, that is creating this outburst of gamma rays. But it was just a hypothesis. You can't ever say a hypothesis is true until you have some evidence to support that. And that actually came with this detection of gravitational waves that was on August 17th of 2017. There is a satellite, a gamma ray satellite called Fermi that is orbiting space. And then there's also the LIGO detectors. And we have been collaborating for many, many years to try to associate a gamma ray burst with gravitational waves. And on this day, we actually did it. And so what you hear is the actual gravitational wave signal. That's it. And then about 1.7 seconds later, there was a detection of gamma rays coming from that Fermi satellite. And the odds of there being a gravitational wave detection within 2 seconds of a gamma ray detection, that is probably not a coincidence. So one of the things you can do to investigate whether or not it's a coincidence is you can take where did the gamma ray burst appear to be to the gamma ray satellite, and also ask LIGO where it thinks the gravitational waves came from. And if those areas where where each detector thinks that the source came from, if they overlap, then it's a high probability that both of these detections came from the same source. So what I'm showing you here, this is the localization for the gamma ray burst from the Fermi satellite. The next is from Fermi and another detector on Fermi called Integral. It gives you a ring on the sky that also overlaps with Fermi. And then LIGO's two detectors, the green areas you see there are where LIGO localized it. And I'm going to pause this real quick. LIGO and Virgo, both LIGO detectors and the Virgo detector was online whenever this data was taken. But the Virgo detector did not see a gravitational wave. And in this situation, the reason that Virgo didn't see it is this particular area in the sky is an area in the sky that the Virgo detector is not very sensitive to gravitational waves, where LIGO is. And so it was expected that Virgo should not have seen it. And we were able to use that information to further refine the area that LIGO said the gravitational waves came from into this smaller area that you see here that's labeled LIGO and Virgo. So inside of this area, there were 49 galaxies that were also in the distance range of about 130 million light years away of where we thought the gravitational waves came from. Traditional telescopes started looking at these galaxies and they ranked them by mass. The more mass a galaxy has, the more stars it has, the more likely it is for something interesting to happen in that galaxy. So this was the third most massive galaxy that you're looking at right here. This galaxy is called NGC 4993, and because it was the third most massive, we found a extra source of light in this galaxy that wasn't there before. This was the source of the gamma rays and the source of the gravitational waves that we observed. This animation here on the left, I'm showing you actual photographs of NGC 4993 throughout the observing of it to study it, to find out more about the system that made these gamma rays and these gravitational waves. Over on the right is going to be a succession of the light curves. Light curves measure the brightness of different wavelengths of light, and it displays those as a graph. So over in this general area, you're going to see a source appear right there. It's initially very blue, and then it fades to red. So whenever this gamma ray burst happened, it was a bright blue event, and then after a while, it faded into a red shine. The light curves that came from this, so this is on a loop. Let's watch it again. So bright blue, and we can see this is blue is on this end, red is on the right end, and then it fades down to become more and more red over time. And these bumps that you're seeing on this light curve, especially the bumps in this general vicinity, these are the signatures of heavy elements being created. And when an astronomer talks about heavy elements, they're usually talking about elements that are heavier than iron, because stars are fusion reactors that are smashing lighter elements together to make heavier elements. But a star can only do that up to iron. After iron, you don't get energy out of that nuclear fusion anymore. It takes energy to make heavier elements. And so a star can't do that and still use that as fuel to maintain its pressure and to keep it from collapsing and then going supernova. However, in the supernova, you can have runaway fusion reactions, which will make those elements that are heavier than iron on the periodic table. And the bumps that are specifically seen here are bumps that are specific to neodymium. And that is important to scientists. What this really says here is that two neutron stars, which is what this was, two neutron stars merged together. Whenever that merger happened, there was a gamma ray burst, and then there was an explosion, and this explosion was called a kilonova. And as that kilonova explosion was happening and evolving over time, it was having these fusion reactions that were making heavier elements. And this was groundbreaking for us, because all the time we've been looking around us and a good example of this is gold. A lot of us have gold jewelry, even if we don't have a lot of it. A lot of us have some gold jewelry. There is more gold in our environment than there should be if supernovas are the only source of gold, where gold can be created. So gold is heavier than iron on the periodic table. So there is more gold around us than there should be. But it turns out that these kilonovas are actually very efficient creators of heavier elements than iron, including gold. Now, we didn't specifically see the signature for gold. We saw the signature for neodymium. But the estimate of how much gold that was made from this, with the frequency of neutron stars merging, the statistics we understand of that, and the number of supernovas, it actually now accounts for the overage of gold that we see. And actually, most of the gold that is around us probably didn't come from a supernova. It probably came from a system like the one we're looking at right here. So if you have any gold jewelry, like a wedding band or anything else, appreciate that. That gold was either created in a supernova, which is awesome, that's cool, or whenever two neutron stars collided and made a kilonova, which is really cool too. So your jewelry is even cooler than you probably thought it was before. And finally, I wanted to just show this summary of our understanding now of how our elements created. So we have this coloration in our periodic table, the Big Bang. So lots of hydrogen and helium and some lithium existed in our early universe. Everything else was made inside of stars. And you can see that these things that are heavier than iron are made either in an exploding massive stars, or lots of things are made in this light yellow color, which indicates that it was made in merging neutron stars. And so you can see over here, silver and gold. Most of the silver and gold and platinum that are around us, that actually, most of it came from merging neutron stars. And so not only is gravitational waves giving us a better understanding of this system, it also provided us the evidence we needed that this was two neutron stars that created that short gamma ray burst, so that we knew it was short neutron stars from the gravitational wave itself, not from the light. And then the light helped us see these elements that were being created. So we got this much bigger picture, and our very first evidence that we needed to support that hypothesis that short gamma ray bursts are actually created whenever two neutron stars merge into each other. It's not necessarily the only way they're created, but it definitely supports the hypothesis. So I've already been talking for an extended period of time. I'm very excited about my research, and I can talk about this all day to anybody who's willing to listen, but I think now's probably a good time for me to listen to any questions you have.
Okay. Thank you, Amber. We have a round of applause for our speaker. I'm going to take the host prerogative and ask a couple things. Well, first of all, I just recently read I guess it was a blog post about the false injection story of, and I gotta say, I would not have been so magnanimous if I had been in that room when they told me, "Oh yeah, by the way, this is all fake."
Well, the interesting thing is so the LIGO collaboration gets together twice a year for our collaboration meeting, where we all of the big talks and sharing interesting results. We get together and we do that. So where they told us it wasn't a real thing, it was at one of these meetings, and I was pretty sure it wasn't a real thing. It seemed too good to be true, and I'm a pessimist, and I like that. Personally, for me, it works because when you're a pessimist, you're usually not too disappointed because you're expecting it. And then whenever amazing things happen, it's even more amazing. So I kind of like this. And that's where I was whenever they were going to announce this. And they spent a whole half of a day going through all of the tests that they did over these 5 months to try to disprove that this was a real gravitational wave. And everything looked good. But I still didn't believe it. But everything looked good. Right before they told us, they actually passed out glasses of champagne. That's whenever I started looking around. Like, I was holding a flute of champagne, and I'm looking around, and I'm like, maybe. And then they did open it. But it was a little bit of a letdown. But at the same time, we proved that we could detect gravitational waves with our current data analysis methods, and we were able to reverse. So we were able to tell everybody what kind of gravitational wave it was and what kind of source made that gravitational wave. So not only could we detect gravitational waves, but we could do astronomy with it. And so that was exciting in and of itself. Although I have to admit, even the pessimist in me was this much disappointed, and the champagne didn't help.
So my question is, you've probably been asked what the bottom of mass range that you can detect is. I'm curious, is there an upper range that LIGO can detect in terms of collisions?
So it all has to do with the frequency ranges that LIGO is going to be most sensitive to. So we're most sensitive from about a few tens of hertz, all the way up to about a kilohertz, 2 kilohertz region. And so that is going to restrict the kinds of signals that we're going to be sensitive to. So we're going to be sensitive to things like stellar mass black holes, like I mentioned before, things like neutron stars, things potentially, we haven't detected these yet, but potentially things like supernova, like core collapse, part of the supernova. Things that are really, really massive are going to move around a lot more slowly. And so an example of that would be the supermassive black holes that are at the center of galaxies. So when galaxies interact and collide, these supermassive black holes will start orbiting each other, and over eons start orbiting each other faster and faster and eventually collide. But the frequency that they collide at is going to be much slower than what LIGO is going to be sensitive to. So we're not going to be able to detect those super massive things. However, there are other gravitational wave type detectors that can. So there is something called nanograv, and nanograv uses neutron stars. There's a special kind of neutron star called a pulsar, and these neutron stars can spin around incredibly fast, and they beam out jets of light out from their magnetic poles. And if that jet of light happens to pass over the Earth, we can detect it. These are basically like the universe's lighthouses, and they spin so fast and they're actually more accurate than the best atomic clock that we have. But we can measure slight changes in the timing of the arrival of those pulses of light from these pulsars. And that could be because of gravitational waves passing between the Earth and that pulsar, actually changing the distance that the light has to travel. And so that is an example of a detector that would be a method of gravitational wave detection that would be able to find these very high supermassive black hole collisions. And since I'm already talking about different kinds of gravitational waves detectors, there's a space-based detector called LISA. It's planned to be launched by the European Space Agency towards the end of this decade, maybe the beginning of the 2030s, but I believe it's on track so far for the end of this decade. And with that being in space, we don't have to worry about vibrations from the ground contaminating our data like we do for LIGO. And we can make the detector almost as big as we want, because real estate in space is free as long as you can get there. So that is another opportunity to detect those lower frequency gravitational waves.
All right. Yeah, I've done my work in optical IR interferometry, basically trying to synthesize larger telescopes to image like stellar surfaces, that sort of thing. And one of our dreams was to actually put an interferometer in space to do that sort of thing, because as you say, because it's space, you can make the thing as large as you want to. But unfortunately, that sort of thing is not as how should I put it, as interesting as gravitational waves, apparently. So we didn't quite get the funding.
Well, the LISA program has been on deck. So whenever I started graduate school in 1999, LISA was supposed to be launched within the decade. And obviously it hasn't. So don't feel bad. We've been waiting for a long time too.
Excellent. Does anyone in here have any questions for our speaker? No? How about anyone online? All right. Well, apparently I know that your presentation was awesome, but apparently it was so awesome, no one has any questions.
Actually, there's one in the chat.
Oh, is there one in the chat? All right. Wow. There we go.
So Aiden asked, are you scared of gravitational waves stacking, like the waves of a black hole collision passing by another black hole before reaching us? And actually, no, not really, because those gravitational waves will interfere like any other wave. So if you have two sound waves that overlapped with each other, they'll interfere while they're actually overlapping with each other. But as they move past each other, they come out unchanged. And so, because of that, these gravitational waves have probably interacted with other gravitational waves on their way to us. And but because of the nature of how interference works with waves, regardless of whether it's gravitational waves, light waves, sound waves, or even mechanical waves, those waves, after they pass by each other, they're fine. We don't have to worry about it. Actually, it's almost sad that they don't carry that information about the other gravitational waves that they've talked to, because then we would be able to extract even more information about the universe if we would be able to tease that out. But that's not something we're able to do.
I did not know that. Mhm.
You're welcome.
Okay, if we could have another round of applause for our speaker. Thank you, Amber. So right now, this is basically new to us. So right now, because of the weather, we will not be able to open up the telescope. And so what we're going to do is I'm going to hand it off to M. Yep, you. Or who is it either going to be you or Patrick? I can't remember. Okay, Patrick is online. Yeah. So Patrick, if you want to share your screen, can you show your screen?
I should be able to.
All right. Amber, if you'd like to stick around, more than willing to watch us go through our telescope tour.
Sure, I'm happy to.
I'm getting an error message. Host disabled screen sharing.
Yeah, that's probably my fault. All right, let me see if I can do this. Participant. Did you? Yeah. I'll just make him a co-host. All right. Good to go. All right, Patrick, before you get started, generally speaking, when we do this, again, we will actually be able to walk you guys over to the observatory and show you what's going on over there. But so, all right, Patrick, take it away.
Okay, so for the moment, we're showing the observatory control computer desktop. And you may notice it's a pretty standard Windows machine. And really a lot of our hardware and software is relatively commercial off-the-shelf stuff. To give a bit of context, with the cameras we have mounted around the observatory, we have these forward-looking various locations, including the interior of the control room in top right, the telescope proper in top left, outer view of the dome on the bottom left, and human track of some of the telescope internals on the bottom right. That if this were an in-person tour, we would be stepping into the control room to show this off directly. But it's not, so we aren't. The telescope itself can be sort of hard to try to get a sense of scale here. It's a 32-inch or 0.8 meter Cassegrain design, which is to say that the diameter of the telescope is 32 inches. And the way it works is that light comes in through the open tube in the front, bounces off the big mirror in the back, bounces off a secondary mirror that's about 12 inches across, that's about at the bottom edge of this mounting bracket, then comes back down through a hole in the primary and into our instrumentation that's also mounted on the back. This is some of our control software in including that it's showing a view of the sky in terms of what's up right now, although unfortunately with the clouds in the way, we can't really show this, but see what stars, planets are there. We can relatively simply search for an object to glue the telescope to that, or even just point in location, ray ascension, declination, if we're dealing with something that's not in the database. Let's see. The telescope itself is the whole optical tube here you see moving is about 1,000 pounds. This fork mount around it is another 1,000 pounds. And the base that's a bit out of the frame of this image is 2,000 pounds. So the whole thing tends to be a bit more than most people's cars. That's something quite slow I wanted. So this is called doing illegal slews because we're actually pointing the telescope too low for it to look out the side of the observatory. That we have a 15-degree limit simply because we can't have the observatory be arbitrarily open. And ultimately, that is because I have to protect it from the weather. Generally don't want to look at extremely high IMRAS as stars are low in the sky because you've seen the way they twinkle and it gets much worse at those distances, at those altitudes. Slower than I'd like. Yeah.
Yeah, I think
Sorry, you had a comment? But beyond that, we have really conventional software, including that drives our CCD, which is a 16.8 megapixel camera, which may or may not sound impressive depending on what your phones have. Mine has about 12 megapixels, so it doesn't sound that much better. I'm being a bit slow here because the way the display is being shared is cutting off some stuff. It's a little bit hard to show the example images we have. It's worth noting that our telescope takes images in black and white by default. So while we can do stuff, sorry, there's a question about how I know what the magnitude of stars are. That to a large extent, that's stars that are first magnitude or brighter will just be in the databases. There aren't that many, so we know where all of them are. And the actual database that telescope has goes down to, I think, at least 12 and a half, maybe farther. Let's see. That this is a good example of default sort of image that we take. This particular one is of a planetary nebula. That is an example of what happens when more or less sun-like stars at the end of its life It's burned through all the hydrogen in its core. It's become a red giant. And then the last stages, it's relatively unstable there, so that there's a lot of pulsations and outer layers get puffed off and float away. So this whole thing is on the order of 2 light years across, even though it just looks like this tiny donut because it's about 1,600 light years away. And it's in black and white because by default, our CCD takes images in black and white, that we don't have a specific color, but all the pixels in it cover a broad range of wavelengths. And so we slide filters in place to choose a specific color. And we actually have a pretty big range. So we can go from near ultraviolet to near infrared. We also have H alpha filter, which you like to use because it's this very specific wavelength that excited hydrogen gas puts out. So nebulae show up great in it. And even though we're in the middle of Fairfax, with all the light pollution that involves, you can see a lot of detail in that wavelength. But these are the sorts of images we take by default. So we will okay, there. It's unresponsive for bits, so we can combine red, green, blue filters to get color images like these. And in this particular nebula, that well, it's really putting out these colors. It's sort of hard to call a true color image. Like when you look through the telescope at this, it's purely there's a grayish ring that I like to describe as a ghost of a Cheerio. That gives an extremely brief overview of what we can do with the CCDs with an example image, but really should try to show a few more pretty pictures. Yeah, this is one that tends to look pretty good. That here we have an image of the moon taken in the U-band filter, that which is to say it's in near ultraviolet. And you may notice it looks pretty normal, except some of the craters are just much brighter than usual. That the very recent fresh craters that have kicked up more or less fresh parts of the lunar surface, they are just more reflective in ultraviolet. And this demonstrates a lot of why we want to take images in wavelengths that aren't visible light, because you just see more things. And if you like search around the web, you'll see things called images of the mineral moon, where they look for the very faint variances in lunar colors, because they show things like there's more magnesium or more titanium or the like. And it's pretty dramatic, just what you can do with a few filters in terms of figuring out what surface composition of a body is. That you may have noticed that the moon didn't entirely fit in the field of view, that our field of view is just a little bit too small for the moon as a whole. So normally we can't do things like take images where there are 2 planets in the same field of view. But in this particular case, back in December of 2020, Jupiter and Saturn were in a so-called conjunction, where they're extremely close in their apparent position in the sky, even though one of these is about twice as far away from us as the other. So we took advantage of that to image in a few different bands and create this color image where you can see Jupiter at the top, 3 of its moons alongside it. I'd have to check exactly which ones are which, as well as Saturn, same field of view. And at the closest, it was sort of hard to actually tell Jupiter and Saturn apart. They looked almost like a single bright object without magnification. I'm mildly concerned that I might be racing through stuff. So if anybody has any questions, just feel free to ask them in chat. I like gloss over something. Right.
I think you can show 1 or 2 more and then we can wrap it up.
Yeah, that this is one where well, the detail isn't always the best because while we have somewhat zoomed in field of view, that we're limited in our resolution by atmospheric scenes, so that can't get great details on the planets. But here, depending on how high the contrast is in screen sharing, you might be able to see the great red spot. That just took advantage of being aware that there was a transit when the students took an image, and we got it. And there's a certain amount of fun usage more or less during downtime of the telescope where students can image what targets they want, as well as some of the classes doing small scale research projects with the telescope. And more generally, we can actually use the telescope for a fair amount of actual research, which is to say detecting exoplanets. Yeah, the cartoon version of an exoplanet that's a planet orbiting another star is that if its orbit is lined up correctly, it will sometimes pass in front of its stars. So that you see it, one where the planet's off to the side, two where it's starting to go in front of the star, and three where it's completely in front of the star, transiting and blocking out a bit of the star's light. Unfortunately, we can't just zoom in on the stars to see this in action. It's sort of like transits of Mercury or Venus, if you saw those, but since we can't resolve stars as disks aside from our own, really, that we can only do things like measure their brightness. And so we do that in practice. It's possible to scan large sections of the sky at a given time, do that and measure what's going on with lots of stars and look for these dips. Because when the planet's around the star, it's blocking off an amount of light that's comparable to the planet's size versus the star's size. And so the size of this dip means that we now know that if it's acting in a way like a planet should, the size of a planet, since it's in an orbit around the star, this dip will have a consistent length and reoccur in a consistent time frame. And because of that, well, with actual data, it looks surprisingly similar to what that cartoon showed. This particular one, we found a hot Jupiter around a planet, around a star that's a little bit smaller than the sun. So this particular one has a 2% dip, which is, it sounds small, but it's actually really huge as far as these things go. That Jupiter around our sun would only be a 1% dip. Earth is only 0.01%, but it is possible to measure. We like this one to show to people because it's a relatively large dip, so it shows out well. Maybe no scatter. Ultimately, our instrumentation's imperfect. Noise exists. We try to deal with as best we can with image processing and the like, but it's there. Also may notice that we have other data sets because we want to measure what's going on with a bunch of other stars in the field of view and make sure it's a real thing. And we knew to look in this time frame because of TESS, the Transiting Exoplanet Survey Satellite, which NASA launched back in 2018, is doing those large-scale scanning of sections of the sky and is finding candidates, but they want other observatories to follow up to make sure it's a real thing and not like a image artifact or a surprise binary star system or the like. So that's an extremely brief version of the research we do here. The science images themselves are not very pretty, unfortunately, so we can just talk about how we have the target star in the center and then various calibration stars around it. I guess, are there any questions about what we do in terms of research or about the pretty pictures or other astronomy related things or telescope related things?
Nothing here. I think we can wrap up now.
Okay.
Thank you, Patrick. Appreciate that. All right, Em, going to escort our guests to go see the observatory. I will finish up here. Amber, again, it was, thank you for being here. Kind of over there, so.
My pleasure.
Thank you. Yeah, thank you again for coming here. This will be posted on our YouTube channel, and so when that does, I will definitely send you a link so you can advertise it as much as you like.
All right. Thank you so much for having me.
Thank you again for having. Bye-bye.